Well, I'm gonna get started. So. Announcements wise. Worksheets 21 through 24 are gonna be due on the 23rd. Homework number 1 will also be due on the 23rd. That's next week, Tuesday. Worksheets 16 through 18 are due on the 16th. And homework number 2 is also due on the 16th. That is, October 16th. So the exam on chapter 1 and chapter 21 through 24 will be on the 23rd in class. It's going to be 60 multiple choice questions. That's what I've worked out for this exam at least. You get 1 sheet of notes that you can use for reference to help with memory. You can use both sides of it, but it needs to be like the size of a regular letter sheet of paper. And the test will be in class on paper using a Scantron sheet is the plan. If you have accommodations, you need to make sure you schedule your test taking with the Access Center. And they'll let me know and I'll make sure they get a copy of the test. I just know there's at least one person in this class who has accommodations. So I'm just mentioning it for anyone who might. Are there any questions about the test? Questions are from the publisher of the book. They're based on the material in the book. I've gone through and made sure they match up with what we talked about in class. So they more or less match up with what we discussed in the slides. But if you read the chapters, you'll be fully informed. So we're beginning on chapter 16, which is on the atmosphere, its composition, structure, and temperature. So we've moved on from space down to the atmosphere. So we'll talk about the difference between weather and climate, and we'll look at the basic elements of weather and climate. We'll talk about what the atmosphere is made of, the gases that make it up, and identify the components that are most important to understanding weather and climate. We'll talk about how to look at a graph that shows changes in air pressure from Earth's surface to the top of the atmosphere, and how to talk about a graph that shows you the atmospheric layers based on temperature. So we'll talk about how pressure varies from the surface to the top of the atmosphere and how temperature varies. We'll explain what causes the sun angle and length of daylight to change during the year and talk about how these changes produce the seasons. So we'll talk about what causes the seasons. We'll distinguish between heat and temperature. And we'll talk about the 3 mechanisms of heat transfer. We'll go over the paths taken by incoming solar radiation, and we'll summarize the greenhouse effect. So we'll talk about how great solar radiation comes in, how it potentially leaves, and we'll also go over the greenhouse effect and what that is. We'll look at 5 commonly used types of temperature data and talk about temperature data using isotherms. We'll look at the principal controls of temperature and use examples to describe their effects. We'll look at patterns depicted on world maps of January and July temperatures to see how temperatures change with the seasons. So, when we talk about the atmosphere, we can talk about what's happening over a short period of time, what's happening day to day. That is the weather. The weather is what's happening today or what's happening this week. It's not like a long-term pattern, it's short-term. The period over which we can predict the weather The short-term things that's constantly changing is about 10 days. There's about a 10-day forecast. That's the reason it cuts off there is because that's more or less our limit of being able to make predictions. For things like rainfall and exact temperature and stuff like that. That has to do with the fact that the atmosphere is a chaotic system in a formal sense. And so small changes can have big effects over longer periods of time. That means that because our data is always going to be kind of incomplete, there's a limit to how far forward our predictions could be. It's such a big, complicated system that we can only predict so far into the future on detailed predictions. So that's weather. Weather is what's happening day to day. Climate is long-term trends. So climate will tell you that in general, it's warming up over a period of years. It doesn't tell you if it's going to be warm today or cold today. That might vary. But it's telling you in general, each year is warmer than the last. That's a climate trend. So it's over a long period of time. You're looking at a generalized composite of weather. You're looking at the long-term, large-scale trends. And climate can give you indications of our stuff that people are doing over longer periods of time, causing things that are going to cause us problems. So graphs can display climate data. So here is the record high, average low, and record low for each month, plotted for a year. So you can see the pattern that occurs in temperature over the months, kind of thing. And you can compare this with other years and see how you can look at how the average highs change over several years, kind of thing. So the elements of weather and climate, these are properties that can be measured regularly. The most important ones that we measure are temperature, how hot it be, humidity, how much water there is in the air, cloudiness, the amount of clouds, precipitation, how much water is falling from the sky, and what kind of water is falling from the sky, is it liquid water or solid water kind of thing, air pressure, the pressure of the air, and wind speed and direction. So those are the kind of things that are regularly measured by, if you have like a weather station, that's what a weather station is measuring. It's measuring things like temperature, humidity, cloudiness, precipitation, air pressure, and wind speed and direction. And if you buy a weather station, it should measure all of these except maybe cloudiness. You can measure temperature, humidity, air pressure on a chip. So that's easy enough. Precipitation is a little trickier, but you just need a rain gauge. And then wind speed and direction, you need a device specialized for that. So the atmosphere, the air we are breathing, is made up of several different gases. It's a mixture of gases. If we look at clean, dry air, and we're going to be talking about clean, dry air because the amount of water vapor in the air varies a lot. So if we want to talk about like percentages, we want to get rid of the stuff that varies a lot. And that's like water vapor. So just in general, if you have air anywhere that is clean, dry air, not got weird pollution being dumped into it, and it's not full of water. This is the stuff that doesn't really vary in air. So nitrogen makes up about 78% of the air. This is N2. So it's diatomic nitrogen. It's two nitrogens bonded together. I don't know why that doesn't have a subscript 2. I will quickly fix that. What? Okay. Sorry about that. I was going to fix that, but that was very much not what I wanted to happen. So apparently this doesn't want to be fixed. So it's nitrogen. It should be N2. But yeah, nitrogen is, and it's a diatomic molecule, it's N2. Oxygen makes up about 21%. That's O2. Two oxygens bonded together. And then about 1% is argon, which is just argon. It doesn't do much. It's a noble gas, so it doesn't react with anything. It just floats around. There's some other gases in there. And then after argon, the next most common thing is carbon dioxide, and that's 0.0405%, roughly. It's going up, so it's probably a bit more than that now. And well, that is a small amount. It does have an important effect in that it absorbs heat energy from the Earth. So it drives the greenhouse effect. So the atmosphere, nitrogen's about 78%, oxygen's about 21%, argon's about 1%. Carbon dioxide is 405 parts per million, 0.0405%. And then everything else, there's about 18 parts per million neon, 5.524 parts per million helium, 1.5 parts per million methane, 1.14 parts per million krypton, 0.05 parts per million hydrogen. Little bits of stuff. Now, over time, at least in the recent history, the carbon dioxide level has been steadily increasing. The red line is the monthly CO2. It goes up and down depending on photosynthesis, basically. In the spring and summer, it dips down because the northern hemisphere has lots of plants that consume CO2, and in the winter and fall, it pops back up because it slows and decay of plant material releases CO2. That's just a cyclic pattern that happens every year. But you can see in general, the trend is the amount of CO2 is going up. And that is, yes.
I just had a question. What type of effects does increasing CO2 have?
Well, we'll get to that, but the main thing increasing CO2 does is that it absorbs infrared radiation released by the Earth when it's heated by the sun, and that effectively traps more heat on Earth and warms the atmosphere. So it leads to warming of the atmosphere. There are other gases that do that as well. Another one that's very common in the atmosphere is water vapor does that quite well. But we like water vapor, and but the additional CO2 coming from burning stuff, it leads to a significant issue. So this is question? Okay. So this is a short video about that CO2 record. So if you look at the CO2 record, if you also look at average temperature, there's a corresponding rise in average temperature. So this is a short video about the CO2 record, the Mauna Loa CO2 record. It's recorded at Mauna Loa in Hawaii. Why did you not start?
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the trend of the Mauna Loa CO2 record and relate it to atmospheric processes including climate change. Scientists have been measuring carbon dioxide levels in Earth's atmosphere for about half a century. A sampling program was set up at Mauna Loa in the late 1950s by Dave Keeling. As a result, this is called the Keeling curve. Basically, what you see here in red are the monthly CO2 levels. The overall trend basically has been smoothed out to take away the seasonal signal, and that's the black line there. So essentially what you see is that every time the graph goes up and then down and then up and then down and up and down, what you're looking at there are seasons. Basically in the northern hemisphere summer, a lot of carbon dioxide is drawn out of the air by plants, and so you get lower levels. In the northern hemisphere winter, most of the plants are not undergoing photosynthesis, so carbon dioxide levels creep up again. And in spite of that seasonal signal, you see that there's this overall trend towards higher and higher levels over time. That increase is of some concern because it represents a perturbation to the climate system. The ice cores that have been collected at Vostok in Antarctica have shown that CO2 levels have varied over the past million years or so from about 180 to around 280 parts per million. And then, starting with the Industrial Revolution, we've completely left that envelope of normalcy, and CO2 levels are at around 395 parts per million right now, and they're climbing fast. If you consider what the Earth's climate is doing, and you only consider natural forces, that basically gives you this blue line that goes across the bottom here. So naturally, we would expect the climate to be more or less stable. However, if you also consider the anthropogenic effects, in other words, the human production of CO2 and other perturbations to the climate system, you would expect to see something in this pink band. And what we actually observe is shown in black. You can see it's right there in the middle of what we would expect if we consider both natural and human forces that are influencing the climate system. Let's wrap up our discussion by traveling down to the South Pole. This is the Amundsen Scott South Pole Station, an American scientific research facility that's located near the South Pole. One of the things that they do here is that they record the level of CO2 in the atmosphere. So what would you predict for the CO2 concentrations at the South Pole as compared to, say, Mauna Loa or some other northern hemisphere location? Take a minute to think about that, and then we'll take a look at a graph. All right, so here's the promised graph. Here's the data from the South Pole. The South Pole line is the line that's shown in black. The blue line is actually from Alaska, from the northernmost part of Alaska, Point Barrow, way up on the Arctic Ocean. So one of the things that you'll notice here is that when Barrow's numbers go up, the South Pole's numbers go down. So basically that's, again, the seasonal signal that we talked about at Mauna Loa. When it's the northern hemisphere's winter and carbon dioxide levels are at their maximum, it's the southern hemisphere's summer. And so the plants there are drawing down CO2 levels. But there aren't a whole lot of plants in the southern hemisphere. And in particular, there are no plants in Antarctica. And so as a result, you see that the overall amount of variation in the South Pole's line is much less than at Barrow. So Barrow has a really big seasonal swing, up and down, up and down, up and down. But the South Pole has a relatively limited seasonal swing. And then, of course, the other thing that you notice here is just like at Mauna Loa in Hawaii, both Barrow, Alaska and the South Pole show increasing carbon dioxide levels over time. Thank you very much for your attention. This has been another Smart Figure.
So, those are the stable-ish components of air. They don't vary day to day. I mean, yes, there's this trend where we're getting more CO2, but it doesn't vary like day to day kind of thing. But there are stuff in the air that don't vary all the time. And the biggest one of those is water vapor, which can be up to about 4% of the air's volume is water vapor. This forms clouds and precipitation. It varies. This can vary quite a bit. It also absorbs heat energy from the earth. And it also, the evaporation of water is one of the big ways the heat is transferred from the earth into the atmosphere. But we don't want to remove water vapor from our atmosphere. That would just generally be bad. But yes, there is water vapor. It's does a lot of things. And when you come to talking about how it affects temperature, it has both helps. There's some things where it will help increase temperature. There's other things that will help decrease. So another common variable thing in the air is aerosols. These are tiny solid and liquid particles. These are important because water vapor can condense on these tiny particles, on solid particles. Also, aerosols can reflect sunlight that help color the sunrise and the sunset, which is why, those days where we're having one of the wildfires up in Canada, sunset can often be a lot more dramatic because there's more aerosols in the air. But you can have situations where you can have significant effects from reflecting sunlight as well. So in the 1800s, I don't remember the exact year off the top of my head, there was a massive volcanic eruption. And it was so significant that, it significantly cooled the whole planet because it dumped so much crud into the atmosphere. Specifically, it had a big effect on Europe. It was called the Year Without a Summer. And yeah, so it was mid 1800s. And also, the fact that it was so miserable led to the writing of Frankenstein through a somewhat convoluted series of events. But yeah, there was this massive volcanic eruption and it cooled the earth for a year or two. So here are some examples of aerosols. They can have very important effects. So like here's a dust storm being thrown up. Down here is air pollution. Turns out a lot of the rain, in a really bizarre sequence of events, a lot of the rain in the Amazon rainforest, part of the process that leads to how it is so rainy there, involves sand being blown from across the Atlantic Ocean in the Sahara. So tiny bits of sand being carried across the Atlantic Ocean and helping to seed clouds above the Amazon. Sort of a complex, strange system. So here's a short video about aerosols. Yeah. So how these videos are. So this is NASA.
Well, an aerosol, the physical definition of it, it's a small particle which is suspended in the air, can be suspended at any altitude, but our main interest is in tropospheric aerosols, which are suspended at altitudes essentially from the ground to about 8 kilometers in the atmosphere. The total number of aerosols in the atmosphere is extremely large. It's like the number of stars in a galaxy. And those are tiny particles. Most of them are invisible to a naked eye, but there are very many of them. Aerosol particles can be natural and can be created as a result of human activities. And so those particles are called man-made or anthropogenic. Natural aerosols can come from all places. For example, desert dust is blown off the surface of the Sahara Desert, the Asian deserts, the Australian deserts. Sea salt particles are produced when ocean waves break. They produce a lot of tiny salt particles. Essentially all kinds of fires produce aerosols. Volcanoes, they throw out a lot of volcanic ash, and those are also natural aerosols. And all kinds of human activities produce different kinds of aerosols, and the most typical example would be sulfate particles, the result of combustion, or soot particles. On average, an aerosol particle is estimated to live for about a week. Aerosols are produced, they're transported, and eventually they disappear because they are rained out, for example. Aerosol particles can differ by their size and by their chemical composition and by their shape. And all these inequalities can be mixed together, and that's what makes aerosols so difficult to study. At any given location, particles of different types and of different origins can coexist. If a particle is, for example, generated somewhere in China, it can be transported to the United States of America. So this transport from different places makes the aerosol population at any given location extremely complex. They have several roles in affecting climate. For one, they simply reflect sunlight back to space, and this effect amounts to cooling of the atmosphere and the surface. But the same particles can also absorb light, and by absorbing light they become warmer and they warm the surrounding air, so this effect is to warm the atmosphere. And how much light is reflected and how much is absorbed depends on the chemical composition of the particles, on their size, even on their shape. There's another effect that aerosols exert on climate because they affect the properties of clouds. And clouds are a major modulator of the amount of energy that reaches the surface and warms it. And so by changing the properties of clouds and precipitation, the aerosols can also affect climate. The most important knowledge that we have is that aerosol particles are extremely complex. So we need to study the distribution of particles globally, and the only way to do that is from satellites. The knowledge about aerosols that we have tells us that the instrumentation on this satellite must also be very complicated, and with this instrumentation we must be able to infer many properties of the aerosol particles from space. And that's the purpose of the aerosol polarimetry sensor, which will fly as part of the GLORY mission. We are not interested so much in their total number as how they are distributed, because their distribution affects local climate, and that's why we need to know this distribution with very high accuracy.
So another variable component of air is ozone. So ozone is O3. So normal oxygen is, regular old oxygen. The nice stable oxygen is oxygen double bonded with another oxygen. Ozone is 3 oxygens and is not completely happy. It's an unstable structure. The distribution of ozone is not uniform. It's concentrated in a layer between 10 and 50 kilometers above the surface. It's formed by interactions with radiation from space, ultraviolet light, and it absorbs harmful UV radiation. So human activity was depleting ozone by adding chlorofluorocarbons to the atmosphere, which basically had chlorine in them that reacted with the ozone and destroyed it. And ozone, on the other hand, while ozone is great in the ozone layer in the stratosphere, because it protects us from ultraviolet radiation, it is not something you want to encounter on the surface of Earth. It's a pollutant at the surface because it damages vegetation. It's harmful when it inhales. It's very reactive. So it will react with you in ways that you don't necessarily like. And it usually gets generated, from very large, electrically, from like large currents and things. And people do use ozone. There are things like ozone generators and stuff, because you can use ozone to sterilize stuff. Because again, it reacts with stuff, it can kill things. But but it can damage vegetation. It's harmful when it's inhaled. It gets produced at electrical equipment, but it can also be produced by when certain pollutants undergo reactions triggered by light. So this is the Antarctic ozone hole, and since the ban of chlorofluorocarbons, the thinning of the ozone layer in the Antarctic has stopped and started to turn around. It's starting to recover. So that's a good evidence that, you know, large scale activity by humans, you know, everybody agrees to stop doing the bad thing, we can actually recover from these things. So in 1979, this was the amount of ozone at the South Pole. You can see it's much thinner here in 2016. But it has actually stopped growing and started to shrink. And people don't talk about it because it was successful. So the so-called ozone hole, which was not actually a hole, it was just a thinning of the ozone layer.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure.
It did cause issues.
After watching this video, you should be able to describe where the ozone layer is, how the hole in it formed, and what the implications are for human health. So if we look at a vertical slice through the atmosphere, we'll see that the atmosphere changes with increasing distance above the Earth. You and I spend most of our lives down in the troposphere, but the layer above the troposphere is called the stratosphere. And about halfway up through the stratosphere, somewhere between about 20 and 30 kilometers above ground, which is on the order of around, call it 15 or 17 miles above the ground, that's where we see a concentration of this molecule called ozone. Ozone is oxygen, but unlike the normal oxygen that's O2 that we breathe every day, ozone is O3. It's actually a health hazard to breathe it, so you wouldn't want to breathe it, but you should be glad that it's up there. The ozone layer protects us from incoming ultraviolet light from the sun. So the ultraviolet light, some of it bounces off that ozone layer and doesn't make it down to the Earth. Some of it still does make it down to the Earth, of course, which is why you can get a suntan if you spend time outside. But the ozone layer filters out some of the incoming ultraviolet light. Now the ozone hole is a thinning of the ozone layer that is most concentrated over the South Pole, but also exists over the North Pole. There was a lot more ozone back in the day, and then it started thinning out around the late 1970s, early 1980s. And you can see that the ozone hole got bigger and bigger and bigger, and then it kind of leveled out around the year 1995 or so. And it's hope that in the future it's going to recover and the ozone hole will get smaller over time and we'll have a thicker ozone layer over the southern part of the southern hemisphere. The reason that the ozone hole stopped getting bigger and stayed about the same size is in the mid-1980s there was a realization that human activity was causing the hole in the ozone layer, that we were releasing chemicals called chlorofluorocarbons, or CFCs, into the atmosphere. And these were used as propellants in spray cans, they were used as refrigerants. So basically when these things were released into the atmosphere, they did two things. One is that they had a reaction with the ozone molecules where they basically ripped them apart. But also these CFCs were really, really stable, so they stuck around in the atmosphere for a very long time. So each CFC molecule could rip apart many, many, many ozone molecules. The ozone hole over Antarctica was a certain size in 1979, but it got to be much bigger than that. This is what it looked like in the year 2012. You can see that there's much, much less ozone over Antarctica. Why does this matter? Well, people in these places are at higher risk of skin cancer, of developing cataracts, and all that extra UV light actually harms the immune system as well. So there's a bunch of negative health effects from it. We should be grateful that this problem isn't worse than it is. If the Montreal Protocol banning the use of chlorofluorocarbons hadn't been enacted, then probably there'd be a lot less ozone up there and a lot more skin cancer around the world. So if you were to go up to, say, 30 miles above sea level, which is somewhere on the order of around 47 kilometers above sea level, what would be the two things that you'd have to worry about most? Well, as you have no doubt guessed, you are going to be above the ozone layer at that point, so you wouldn't have the protection of the ozone layer, so you'd need to wear some sort of protective clothing to shield you from the ultraviolet light from the sun. You wouldn't have to worry too much about the temperature, because the temperature actually, after decreasing throughout the troposphere, rises again through the stratosphere and basically reaches a maximum there at the top of the stratosphere. But you'd have to worry about oxygen, because you may be aware there's less oxygen the higher you go in the atmosphere, and even climbers at the top of Mount Everest often use supplemental oxygen, and you'd be many times higher than the top of Mount Everest. Hopefully you thought about those. Maybe there's some other hazards that I didn't cover, like that meteor there. But at any rate, I thank you for your attention. This has been another Smart Figure.
You know, your biggest worry would be the lack of atmosphere. Because the atmosphere gets thinner as you go up, and there's very little up by that point. In fact, that's the next thing we're going to discuss. But yes, there's a layer of ozone in the stratosphere. So, one of the things that happens as you travel upwards in the atmosphere is the pressure changes. The pressure of the atmosphere, there's a pressure of about, down here, it's 14.7 pounds per square inch of pressure. So every square inch of your body is receiving 14.7 pounds of force from the atmosphere. And that's just the weight of all the air above you. So the pressure is the weight of all the air above you. It packs the air denser lower down, and it's thinner higher up. And so that means like half the atmosphere is below 5.6 kilometers. And 90% of the atmosphere is below 16 kilometers, 10 miles. So pressure steadily drops as you go up. The air gets very thin. And yeah, the point where you need supplemental oxygen is up, top of Mount Everest. You need supplemental oxygen to continue to survive. It's not going to immediately kill you, but it's a long-term effect. You can't stay there an extended period of time. Because there's just not enough oxygen for your body to function. And then as you get higher and higher, it's thinner and thinner. And in the bottom part of the atmosphere where we live and where all the weather happens and stuff, the temperature drops as you go up. It gets colder the higher you go up. You may have experienced this at some point. Air temperature drops with increasing height. So as you saw in the previous Smart Figure, there was that graph that showed temperature varying. That changes as you get into other layers of the atmosphere. That's how those layers are defined. So here's how the air pressure changes. So down atmospheric pressure is around 1,000 millibar. It's a little bit higher than that, but it's like 1,013 if it's standard. But that's 1 bar is 100,000 pascals, which is newtons per square meter, which are much smaller units. But a bar is a nice round unit in the metric system that is close to an atmosphere. Weather stuff tends to be measured in millibars because the day-to-day variation of pressure is on the order of plus or minus about 20 millibars. So it's a nice unit to work with. And you're working around 1,000. So as you go up, you get to the top of Mount Everest, the pressure is only 314 millibar. You're dealing with something like a third of the air. Captain Canada of the USAF, this was at one point, I think, the record for highest jump. The air pressure was 9.6 millibar. He had to be in a basically a space. half the atmosphere lies below this line. 90% of the atmosphere lies below this line. Just gets thinner and thinner as you go up. So the bottom layer of the atmosphere is called the troposphere. The troposphere is defined by the fact that the temperature decreases with altitude. This is called the environmental lapse rate. It's about 6.5 degrees Celsius per kilometer, or 3.5 degrees Fahrenheit per 1,000 feet. That's the average. It varies from place to place. The thickness of the troposphere varies. It's generally about 12 kilometers. And the outer boundary of the troposphere is called the tropopause, because it's the end of the troposphere. Above the troposphere is the stratosphere. The change from the troposphere to the stratosphere is that once you enter the stratosphere, instead of going down, temperature starts to rise as you go up. This is because the stratosphere contains the ozone layer, and as that ozone absorbs ultraviolet light, it heats the atmosphere. So it warms the stratosphere. So this goes from about 12 to about 50 kilometers. The outer boundary is named the stratopause. This is also where that maximum ozone concentration is. Above the stratosphere is the mesosphere. In the mesosphere, the temperature decreases again as you go up. This goes from about 50 to about 80 kilometers. The outer boundary is named the mesopause. And then lastly, there is the thermosphere, which is above the mesosphere. So from about 80 kilometers up. It doesn't really have a well-defined outer limit. Sometimes people talk about an exosphere beyond the thermosphere, but basically this is a tiny fraction of the atmosphere's mass, just as the atmosphere sort of peters out into space. The gases in it are moving at high speeds and they're heated up. They're very, very thin, but they're heated up by the direct illumination of the sun. So all the stuff like high energy stuff from the sun gets absorbed by the thermosphere directly. So things like gamma rays, all X-rays, stuff like that, just stuff the atmosphere naturally absorbs. So that it's actually warms up again. And so things like auroras happen in the thermosphere. The International Space Station is technically in the thermosphere. Meteors happen sort of in between, in both the thermosphere and the mesosphere. The mesosphere is where it starts to get thick enough for meteors to really start to show up. And you can see the temperature goes up, down as you go up through the troposphere, up in the stratosphere, down again in the mesosphere, and then up again in the thermosphere. But here it's so thin, you start getting into that, some of the fun things like you can get in space where it can be technically very hot and you can freeze to death. Because the stuff around you is very hot, but there's so little of it, it transfers almost no heat to you and you emit more heat. And so you end up cooling down. Stuff can be very confusing when you're dealing with very thin or near vacuum situations. In the Earth and the Sun, let's talk about the relationships between the Earth and the Sun and how things move. The Earth rotates on its axis and revolves around the Sun. Now, the Earth rotates on its axis. The axis that the Earth rotates on is tilted with respect to the plane that it revolves around the Sun in. It's at an angle, which means the portion of the Earth that's sort of facing the Sun changes throughout the year. So the seasons are a result of the changing angle of the Sun and the changing length of daylight, because the Earth is The Earth is tilted, as you can see. This is about the right angle. It's tilted by 23.5 degrees. And so sometimes the sun is coming in on this side and is illuminating more of the northern hemisphere. And sometimes the sun is coming in on the other side and is illuminating more of the southern hemisphere. I might have been, actually, I got those backwards, but that's basically the idea. Sometimes, because of the tilt, sometimes the North Pole is pointed more towards the sun and sometimes it's more pointed away. When it's pointed more towards the sun, we get summer. When it's pointed more away, we get winter in the northern hemisphere. So over the year, the angle of the sun in the sky changes. During the summer, peaking at the summer solstice around June 21 and 22, 21st or 22nd, we'll have the highest altitude of the sun. So this is the summer solstice at 40 degrees latitude. We are a little bit north of 40 degrees latitude. We're like 41. So that's pretty close to us. Highest angle will be 73.5 degrees up above the horizon. And that'll have the longest day. At the spring or fall equinox, the sun will be at 50 degrees up above the horizon. And we'll have an equal length day and night. That is what equinox means, equal night, equal length day and night. The solstice is when the sun stops, furthest it goes up. And then the winter solstice is when the sun is at its lowest. That's the shortest day of the year. And if you're at 40 degrees north latitude, on the winter solstice, which will be December 21 or 22, the sun will be at about 26.5 degrees. And people tend to put stuff like holidays, religious festivals near the solstices or on the solstices. There's been a little drift. So certain holidays that used to be exactly on the solstice have moved off because of calendar, reforms of the calendar and such. But Christmas used to be on the winter solstice because the traditional Roman winter solstice was on the 25th. That's part of why Christmas is on the 25th, because it was the solstice. But because fixing the calendar several times has led to the solstice to move off of the 25th and is now about the 22nd. And changes in the sun's angle cause variations in the amount of solar energy that reaches the Earth's surface. So the higher, if you're near the equator and the sun is coming directly, is 90 degrees from the surface, you get lots of sun. So for the same sunlight, at 90 degrees, every unit of distance, every unit of sunlight is spread over 1 unit of ground. But if you're at 45 degrees, every one unit of sunlight gets spread over 1.4 units of ground. And if you're down at 30 degrees, every 1 unit of sunlight gets spread over 2 units of ground, which is why it's colder near the poles. Because that sunlight gets spread out over a larger area. So basically each unit of Earth gets less sunlight. So here is a short video showing the effect on how the angle of the sun influences solar intensity.
At the equator, incoming sunlight hits the ground straight on. So 1 unit of sunlight is spread over 1 unit of ground area. It hits at a 90-degree angle. But at other latitudes, the story is different. At mid-latitudes, that same 1 unit of sun is spread out over a larger area, 1.4 units, say, when it hits the ground at a 45-degree angle. In the far north, that same unit of sun might be spread out over 2 units of ground if it hits at, say, a 30-degree angle. Let's use an analogy, a flashlight. The flashlight's putting out a constant amount of light, but if you change the angle between a desk and the flashlight, you'll see that that light is spread out over a larger area.
And if you do this with a flashlight, you'll see that effectively dims the light because you spread it out over a bigger area. And that means the places that get less light per unit area are cooler because they get heated up less. So the Earth's axis is inclined about 23 by 23.5 degrees. The axis always points in the same direction to the effective precession. It does actually change what star it points at over a period of something like 26,000 years. But for our day-to-day life, it always points in the same direction. It points towards the North Star. But the sun is not always in the same place relative, the same direction relative to the Earth, because we're moving around the sun. And this tilting, this change of where the sun illuminates causes the seasons. So just the seasons are not caused by variations in the distance of the Earth from the sun. Just to clear your mind, the point where the Earth is closest to the sun happens to occur in January. And the point where the Earth is furthest from the sun happens to occur in July. So no, the variation in the distance of the Earth from the sun really has minimal effect on the seasons. There are some special days. These are all going to be based on the Northern Hemisphere because we live in the Northern Hemisphere. The truth of the matter is most people live in the Northern Hemisphere because there's significantly more land in the Northern Hemisphere than the Southern Hemisphere. So we'll do this with a Northern Hemisphere bias. The summer solstice is the longest day of the year. Sun's vertical rays are located at the Tropic of Cancer. That is 23.5 degrees north latitude. So that is, should be marked on here. Like this height does pass through Hawaii. And the winter solstice, so that's when the sun's vertical rays are the furthest north they're going to get. The winter solstice is December 21 to 22. And it varies from year to year because there's not a perfect exact number of days in a year. Each year is about 365.25 days. So whether it's the 21st or the 22nd will vary. The sun's vertical rays are located at the Tropic of Capricorn. That's 23.5 degrees south latitude. So it's down here. It's usually marked with a dashed line on a globe or on a map. And that'll be the shortest day of the year in the Northern Hemisphere. In the Southern Hemisphere, the summer solstice is in December, the winter solstice is in June. They just switch. But we're going to talk about the Northern Hemisphere. Then there are two equinoxes. The equinoxes are days when the sun is directly over the equator. They're days when the entire Earth gets equal day and equal night. The day and night are of equal length. So the sun's vertical rays are located at the equator. The autumnal equinox is September 22nd or 23rd. And the spring or vernal equinox is March 21st or 22nd. So the sun's vertical rays are located at the equator in both of these. They're halfway in between the solstices. And the day will be exactly 12 hours long and the night will be exactly 12 hours long. So as the Earth travels around the sun, the side of the hemisphere of the Earth that's more pointed towards the sun changes. When the northern hemisphere is pointed towards the sun, it gets summer. When it's pointed away from the sun, it gets winter. So here's a short video about those Earth-Sun relations.
You should view this animation several times, paying attention to different details of Earth-Sun relations. Notice that the months of the year are shown along the bottom of the screen. The change of seasons. The changes in day length and the angle of incoming sunlight that characterize the annual march of the seasons are due to four characteristics of Earth in its relationship to the Sun. Earth orbits around the Sun, completing one revolution each year. Earth spins on its axis, completing one rotation each day. Earth's axis is tilted relative to its orbital plane, maintaining an inclination of 23.5 degrees from the vertical. Finally, Earth's axis always points in the same direction relative to the stars, a characteristic known as polarity. 4 days of the year deserve special attention. The March equinox occurring around March 20th, the June solstice occurring around June 21st, the September equinox occurring around September 22nd, and the December solstice occurring around December 21st. The animation begins on the March equinox. As you view the animation this time, notice that because Earth's axis is inclined and always pointing in the same direction, on the June solstice, the North Pole is leaning most directly toward the Sun. 6 months later, on the December solstice, the North Pole is leaning most directly away from the Sun. This is the fundamental cause of the change of seasons. Latitude receiving vertical rays of the Sun. When you view the animation once more, look for the latitude receiving the vertical rays of the Sun. The Earth Profile animation box lets you see the angle at which sunlight strikes Earth. But keep in mind that the primary animation correctly shows Earth maintaining constant inclination throughout the year. On each of the 4 special days of the year, the Sun's rays are perpendicular to the Earth's surface at different latitudes. In the animation, labels appear indicating the latitude receiving the vertical rays of the Sun, as well as labels to indicate the length of day at various latitudes. On the March equinox, notice that the equator receives the vertical rays of the Sun. On the June solstice, the Tropic of Cancer receives the vertical rays of the Sun. On the September equinox, the equator again receives the vertical rays. On the December solstice, the Tropic of Capricorn receives the vertical rays. Length of day. As you view the animation again, look for the changing patterns of daylight around the world. While the equator experiences equal lengths of day and night throughout the year, all other latitudes experience variations in day length. The location of the circle of illumination, the dividing line between day and night, determines the length of day at each latitude. On the March equinox, all locations on Earth experience equal day and night. As Earth orbits toward its June position, notice that the length of day is increasing in the northern hemisphere and decreasing in the southern hemisphere. The June solstice is the longest day of the year in the northern hemisphere and the shortest day of the year in the southern hemisphere. On the September equinox, day length is once again equal around the world. On the December solstice, the northern hemisphere experiences its shortest day of the year, while the southern hemisphere experiences its longest day. As you view the animation one final time, notice the pattern of day length near the North Pole. On the March equinox, the Sun rises at the North Pole and will remain above the horizon there continuously for the next 6 months. Following the March equinox, notice that the region in the Arctic experiencing 24 hours of daylight grows week by week. On the June solstice, 24 hours of daylight are experienced from the North Pole to the Arctic Circle. After the June solstice, the region in the Arctic experiencing 24 hours of daylight diminishes week by week until the September equinox, when the Sun sets at the North Pole and will remain below the horizon for the next 6 months. Following the September equinox, the region in the Arctic experiencing 24 hours of darkness grows week by week until the December solstice, when it extends from the North Pole to the Arctic Circle. After the December solstice, the region in the Arctic experiencing 24 hours of darkness diminishes week by week until the March equinox, when the sun once again rises at the North Pole.
So, sort of, there are seasonal changes in the sun and length of daylight. You know, the longest day is in the northern hemisphere is at the summer solstice in June. Shortest day is the December, the winter solstice in December. And you'll have equal length day and night at the equinoxes in March and September. And we're actually coming up on the September equinox. It'll be at the start of next week. So here's another short video about solstices and equinoxes and how they work.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to define a solstice and distinguish it from an equinox, and describe how both days relate to the orbit of Earth around the Sun. One of the most fundamental facts that you need to know about how our planet works is that our planet orbits the Sun in a plane. That plane is sometimes called the ecliptic, or sometimes it's referred to as the plane of the solar system. But the axis around which our planet spins, the axis of rotation, is not oriented 90 degrees to the ecliptic. So here in this picture, that line's like 90 degrees to the ecliptic, but you can see that our axis is at an angle relative to that. That angle is around 23.5 degrees. This axial tilt is the reason for the seasons. In the northern hemisphere summer, you have the northern hemisphere tilted more towards the sun. So that's what's shown over here in the upper left image. The polar regions here are getting 24 hours of sunlight per day because they're always in the sun. And at the equator, there's around 12 hours of sunlight per day, while down in the southern hemisphere, there's less, like 9 hours in Buenos Aires, Argentina, for instance. Now, if you go and you think about the opposite situation, the winter solstice in the northern hemisphere, you see the exact opposite situation. Down there in Antarctica, they're getting 24-hour sunlight. In those circumstances, the equator is still getting about 12 hours of sunlight. And up in the northern hemisphere, in North America, for instance, where probably most of us live, they're getting about 9 hours of sunlight, and then the rest of the day is dark. The midpoint between these two extremes is considered the equinox. The word equinox means equal night, and that means that the day is equal in length to the night. During the equinox, the sun's rays come in from the side, parallel to the lines of latitude, and you can see that all over the face of the Earth there, we're getting 12 hours of sunlight for that one day of the year. So this relates to the orbit of the Earth around the sun because that axis is always oriented in the same direction. So that's over towards the North Star, that'd be up over here somewhere, and you can see that that north polar axis is pointing in that direction. When the northern hemisphere is pointed away from the sun, that's the winter solstice. When the northern hemisphere is pointed towards the sun, that's the summer solstice. So longest day of the year over here on the left, shortest day of the year on the right. And then in between are the equinoxes. So here's one equinox and here's the other. There's one equinox in spring and one equinox in fall. And those are the days, of course, when the day is equal to the night. So let's go back to this image we started with here. Which day of the year is depicted in this image? Hopefully you notice that the proportion of sunlight in the southern hemisphere is much, much greater than the proportion of sunlight in the northern hemisphere. So that must mean that it's the southern hemisphere's summer solstice, and that's the northern hemisphere's winter solstice. Good job. Hope you figured that out. Thanks a lot for your attention. This has been another Smart Figure.
So, continuing on, let's talk about heat, energy, and temperature. So, heat is energy in the movement of tiny stuff, movement of atoms and molecules, and they're jiggling. Heat will always be transferred from warmer objects to cooler objects. So temperature is sort of defined as the direction, higher temperature objects, heat flows from higher temperature objects to lower temperature objects. And there are a few mechanisms for heat transfer. There is conduction through molecular activity. This is the simplest way that heat can be transferred. Two things are touching, the jiggling parts of one encounter the jiggling parts of the other. They whack them, they warm up the other one. This is the heat transfer you get when you touch something hot. Or what happens when you put like a pan on an electric stove. The electric stove is hot, your pan heats up. No, that's not actually completely correct. But yeah, if you put a pan on something that is hot, that's how and it's how the pan transfers heat to stuff in the food in the pan. There. That's just conduction. Heat transfer when things touch. And there's convection. Convection is how heat is transferred by mass movement within a substance. So things have to be moving. Usually when we talk about conduction in like weather or large scale systems, we talk about vertical movements like warm air rising and cool air sinking. And that creates cycles that move air around and that transfers heat. But you can have forced convection. You can move air around to move heat. So if you've got like a heater in your car, your heater blows air over your engine, which is hot, and that air is moved into the body of your car to warm it up. That is heat transfer through convection. And then the last way that heat can be transferred is by radiation, by electromagnetic radiation. If you've ever used like an infrared space heater, where you just like stand in front of it, it sort of glows, or like a toaster. Toasters primarily transmit heat by radiation. They get a wire really hot and it glows, and that's mostly emitting infrared radiation, infrared light. That's electromagnetic radiation. It travels at the speed of light, 300,000 kilometers per second in a vacuum. And that can be absorbed by other things. Anything with a temperature will emit radiation, so that will be another method of heat transfer. So you can stop conduction by not having your thing touch anything, so vacuum stops conduction. You can stop convection by removing the ability of the stuff to move, or by, again, removing the material. And to stop radiation, you basically have to reflect the radiation back. So if you have like a thermos bottle, or something like this cup, there's an evacuated layer in between the inside and the outside of this cup. And that stops conduction and convection, and it's reflective, so it bounces back radiation. So the three methods of heat transfer are radiation, the emission of heat just from as electromagnetic radiation gets absorbed. Convection, heat being carried by a moving substance, like the boiling water in this pot. And conduction, heat just traveling through something. And so things like air does not conduct heat very well, but you can move the air around pretty easily, and that leads to convection. So a lot of insulation uses the fact that air doesn't conduct heat, but uses something that keeps the air from moving around. So foam or down or lots of things like that holds the air in place so that it can't move away and be replaced with cold air or hot air, as the case may be. So these are the three mechanisms of heat transfer.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to name and identify the three mechanisms of heat transfer. So imagine this situation. You're holding a metal pot of water over a campfire. This is a situation that illustrates all three mechanisms of heat transfer. For instance, the handle that you're holding may start to get very hot. You can see it changing to a red color there. It's redder closer to the pot, and it's still its steely gray color over by your palm. But basically, we've all felt this, where heat gets transferred along some material that's good at conducting heat, and metal is really good at it. Other materials like wood or styrofoam, they're not as good at transmitting heat through the material. So that's conduction. A second form of heat transfer is taking place in the pot. Warm water is rising in the middle of the pot because it's less dense than the surrounding water. That pushes other water out of the way, and so it sinks along the sides of the pot, where it gathers heat at the bottom and then rises because it's less dense. So the physical movement of material as an agent of transmitting heat from point A to point B, that's called convection. The third mechanism of heat transfer is what you feel when you make a campfire and stand close to it. You can feel the heat that's being given off by the fire, even though there's not necessarily convection transmitting that heat to you, and there's not a material that's transmitting it to you like conduction. So what's going on here is radiation. The heat is being radiated out from the fire, and radiation can occur without any substances at all. It can occur through empty space. For instance, the energy that we get from the sun every day, that's radiation energy leaving the sun. Okay, let's see. What do we got in this picture? Have we got conduction, convection, or radiation? This is a lava flow in Hawaii. You can imagine that these guys are feeling the heat, that there's some heat being given off from this lava flow, and they don't want to get too close to it. So this would be an example of radiation. What about when these pillow basalts erupted into the seawater? They instantly chilled because the heat was conducted away by the water. So the water transmits heat very, very efficiently, and that's why when you burn yourself, you should run your hand under cold water, because that water is really good at conducting away the heat. Lastly, let's take a look at this section from our discussion of plate tectonics earlier in the text. What would this be an example of? Hopefully you said convection. So convection is the warm rock is rising, and then the colder rock is sinking, and that sets up these currents in the mantle where they basically drive plate tectonics. Good job. Conduction, convection, and radiation. Good stuff to know about. Thanks a lot for your attention. This has been another Smart Figure.
So all three of those happen all the time. Sometimes we enhance one of them to try and make things happen better. If you've ever used an air fryer just uses increased convection by running a fan to cook food faster. It moves more air, more hot air past the food, so it transfers the heat faster. So radiation consists of different wavelengths. You have, from gamma rays that are very short waves to radio waves that are very long waves. Visible light is in the middle, and it's the only portion we see. There's a few laws generally covering how things emit radiation. All objects emit radiant energy. Hotter objects radiate more total energy, and hotter objects radiate more energy as short wavelengths. And objects that are good absorbers of energy are also good emitters of energy. Those are the basic rules for radiation. And the electromagnetic spectrum is all of light, and it varies from high frequency short wavelengths at gamma rays down to low frequency long waves at radio waves. And when we're talking about heat, we're mostly interested. So the sun dumps in stuff centered around, well, green, into the atmosphere. The shorter wavelength stuff gets absorbed in the atmosphere. It gets absorbed by the earth, and it's re-emitted in the infrared. So the heating of the atmosphere comes from incoming solar radiation. And the atmosphere is largely transparent to incoming solar radiation. And then there's a few atmospheric effects that affect how much makes it to the ground and gets absorbed, or gets absorbed. There's reflection or albedo, which is the percent reflected. So clouds, for example, are very good at reflecting away light. White things, lighter colored things reflect away light. There is scattering. Light will be scattered. This is why the sky is blue, because shorter wavelengths get scattered more than longer wavelengths. And then lastly, there's absorption. Some of the incoming radiation will be absorbed by the atmosphere. Some will be scattered. Some of that will be scattered down towards the Earth. Some will be scattered away back into space. Some will be reflected away. Most of the visible radiation reaches the surface. And about 50% gets absorbed at the Earth's surface. Some of it gets reflected at the surface. And sometimes more will be absorbed, sometimes less will be absorbed. And you can usually tell when more is going to be absorbed. That's when you have darker surfaces. And when you have lighter surfaces, more is reflected. Which is why, you know, asphalt roads get really hot on a sunny day. So there's about, of the 100% of solar radiation that comes in, about 5% gets scattered back into space by the atmosphere. About 20% is reflected from the clouds. About 20% gets absorbed by the atmosphere and clouds, and about 50% of direct and diffuse radiation is absorbed by the land and the sea. And then about 5% is reflected away from the land-sea surface back into space. So the Earth reflects about 30% by reflection and scattering, while say Venus reflects like 70% of the light that hits it. And darker areas on the surface absorb more than lighter areas. I think that's where we're going to stop for today, because I don't think we have time for the solar radiation pass thing. But so we're heating the atmosphere. Okay.